Hi, ladies and gentlemen. We are looking at Notes 2.2, Instantaneous Rate of Change. So this is going to be a continuation of our discussion that we had today in class. Today we discussed the difference between average rate of change and instantaneous rate of change graphically, what it means on a graph, okay? But I want to get into how to actually find instantaneous rates of change in this lesson. So what is rate of change? Well, rate of change is just going to describe how one quantity changes in relation to another. Okay. Also, a really key piece of information is that the rate of change is just the slope. Okay, what type of slope it is depends on whether it's the average rate of change or the instantaneous rate of change. So we will use the acronym AROC for average rate of change, and we will use the acronym IROC for instantaneous rate of change. So let's just make sure that we truly understand the difference between average rate of change and instantaneous rate of change. So if I were to give you an example right here, where I have some type of curve. It doesn't matter what my curve is, it's just any curve. So my curve looks, I don't know, like this, okay? And I want to know what's the rate of change from my point A to my point B right here, okay? Well, A will line up with my graph right here at this point right here. This is called f of a, right? And remember, f of a is just your y value. We've got x here, we've got y here, okay? And then b will line up with my graph, and I should probably extend this a little bit so we can see and actually discuss this. So b will line up with my graph at f of b. Okay, and the average rate of change is simply going to be the secant that connects these two pieces here. So basically, I just want to know what is the slope of this line, right? So right here, we're just going to say that the slope represents our average rate of change. So remember, our average rate of change is over an interval, okay? That's really important. And our interval is from A to B. Okay? All right. So our average rate of change, we already discussed this in our last video. Our average rate of change is just simply our slope. So it's delta y over delta x, or change in y over change in x. Or we could just do f of b minus f of a over b minus a, which is essentially just the slope formula. Remember, the slope formula is y2 minus y1 over x2 minus x1, but this is the proper notation we use when we find average rate of change. Okay? So now that we know graphically what average rate of change means, let's talk about what the instantaneous rate of change means. So our instantaneous rate of change is not along an interval. Our instantaneous rate of change is always going to occur at a certain value, not over an interval. So usually we say it's at x equals a. Okay, so let's draw a similar curve to what we have in our average rate of change. So this is what my curve looks like, but this time I just want to know what is my rate of change at A. Still need to figure out what f of A is right here. So this is still f of A. That's still important. But the most important piece is that what ends up happening is we draw a tangent to our curve. And remember, our tangent just intersects our graph once. So our instantaneous rate of change is the slope. So actually, that's right. that our instantaneous rate of change is the slope at A is the slope of the tangent line. To the curve at x equals A. Okay, and your A can change, right? So it doesn't have to be right here. So for example, if my A was right here, then my my tangent line would look like this. So my average rate of change here would be 0. Okay, so remember there are multiple places where we can have our average rate of change. Okay, so here, this is where A would be. Our tangent line would be right here. So our average, or excuse me, our instantaneous rate of change changes as A changes right here. Okay. Let's take a look at this question right here. The population of a small town appears to be growing exponentially. Town planners think that the equation P of t equals 35,000 times 1.05 to the power of t, where P of t is the number of people in the town and t is the number of years after 2000, models the size of the population. Estimate the instantaneous rate of change in the population in 2015. So if you notice right here, it says to estimate it. And the reason why we're going to estimate it is because there's no way to get an exact answer for this problem without using calculus and something called limits. So since we don't know calculus or limits yet, we are going to do an estimate of our instantaneous rate of change, of our instantaneous rate of change. So remember, any rate of change is always going to be our change in y over our change in x. But I'm using p and t because p represents y and t represents x. Okay, so what I'm going to do is I want to find my average rate of change, my instantaneous rate of change. We know this is going to be an exponential function, so we know it's going to look like this. And I want to find it when x is 15. Okay, so if I find it when x is 15 right here, let's say this was 15, here's my my y value. I want to find this slope right here. But in order to do that, what I'm going to do is I'm going to limit it from an A value and a B value and find my average rate of change, and that'll get close to my tangent line. So what I'm going to do is, since I'm going to do an interval, I'm going to do a little bit above 15 and a little bit below 15. So my interval is going to be from 14, let's just try from 14 all the way to 16. Okay, so remember, to find delta P, I'm going to do P of 16 minus P of 14, and then to find delta T, I would just do 16 minus 14. So this is going to be my instantaneous rate of change, but since it's an estimate, I'm going to say it's approximately equal to this. Okay, so let's go ahead and calculate our values. So when x is 16, I'm going to figure out that my answer is 35,000 times 1.05 raised to the power of 16. And we get approximately 76,401. Okay, so we're going to say this is equal to 76,401. And then I'm going to do the same thing for 14. So I'm going to do 35,000 times 1.05 to the power of 14. And I get approximately 69,298. And then that's going to be over 16 minus 14. So I get 7,103 over 2, which is equal to 35,551.5 people per year. So right now that means that my instantaneous rate of change is approximately this answer right here. Okay, but I wonder, well, can I make it a little bit more accurate? Instead of using a difference right here of 1, right? So technically what we did is we did a difference of one above and one below, let's make it even smaller. So let's use an even better interval, because the smaller our interval is going to be, the more accurate our answer is, because the smaller we make it, the closer it gets to the tangent line that we're looking for. So that's what this is saying right here. The smaller your interval is for your average rate of change, the closer you'll get to the instantaneous rate of change. Okay, for the estimate for your instantaneous rate of change, you get closer to the tangent line. All right, so let's do an even better interval. Instead of using a difference of 1, let's use a difference of 0.5. So let's go ahead and figure this out from 14.5 all the way to 15.5. So that means that my instantaneous rate of change is approximately P of 15.5 minus P of 14.5 over 15.5 minus 14.5. Okay, and we have our equation right here. I need you to pause the video and really try this on your own. Find these values that we need to find right here. Find the instantaneous rate of change estimation, and come back to me when you're done and check your answers to see if you agree. Okay? So when you plug in your information, you should get 74,559 minus 71,009 all over 1, which gives you 35,500 or 35,050 people per year. This is a more accurate approximation. And we can make it even more accurate by making our interval even smaller. We're not going to do that, but I just want to talk about a more accurate interval. So right here, we would say a more accurate than that would be if I had my interval maybe 14.9 is less than or equal to t is less than or equal to 15.1. So again, the more accurate you have, or sorry, the smaller your interval, the more accurate your answer is going to be for your average rate of change. Okay? So let's go ahead and talk about, there are two different strategies to use for finding instantaneous rate of change. The first strategy is called the centered strategy. So that's the interval that we're talking about. Okay, and all you need to do is find the average rate of change on the interval from this value right here to this value right here. Now, what does this mean right here? Well, if we want to find the instantaneous rate of change at A, right here, what we're going to do is we're going to do our average rate of change a little bit less than A and a little bit more than A. So you're looking for small values of H. Okay? To find the average rate of change in another way, this way right here is going to lend its way to calculus right here. So we're going to find the rate of change for a small h value again, where we're not going to do an interval a little bit above and a little bit below. We're just going to do a little bit above. So right here, if I'm trying to find it at A, f of A, remember this is x, y, right? Then it's going to be a little bit above A. So we're going to do A plus H, a little bit above A, and then the f value at this point, at this x value right here. So to find it, we're going to do delta y over delta x, which is f of A plus H, right? Because this is my f of B right here, minus f of A right here, all over my B, which is A plus H, minus this one right here, which is A. Okay, so that means that another way to find my average or my instantaneous rate of change is to do f of A plus H minus f of A all over H. And this is something you're going to be using quite a bit when you are in calculus. So essentially, this is the same thing right here as what we're doing here, except here we're going a little bit below and a little bit above. Here we're just going from the actual value to slightly above. That's it. Okay, so let's go ahead and read through this question right here. It says the volume of a cubic crystal grown in a laboratory can be modeled by V of x is equal to x cubed, where V of x is the volume measured in cubic centimeters and x is the side length in centimeters. Estimate the instantaneous rate of change in the crystal's volume with respect to its side length when its side length is 5 centimeters. Okay? So remember, the smaller the h value, the better, more accurate our estimation of our instantaneous rate of change is going to be. So this time I'm going to make my h value, let's make it 0.1. So I'm going to say h is 0.1. Well, if my strategy is going to be strategy number 1, which is our centered strategy, I need my interval. So my interval is going to be slightly less than 5, 0.1 less than 5, so it'll be 4.9, okay? All the way to 0.1 more than 5, so from 4.9 to 5.1, okay? So that means that my instantaneous rate of change is equal to delta y over delta x, which is approximately f of 5.1 minus, let's make this clear that it's 5.1, minus f of 4.9 all over 5.1 minus 4.9, okay? So that's approximately equal to, let's go ahead and calculate this, 5.1 raised to the power of 3 is 132.651, and then 4.9 to the power of 3 is 117.649, and that's going to be over 5.1 minus 4.9. Okay, so that's approximately equal to 132.651 minus 117.649 gives me 15.002, excuse me, over 0.2. So then that means that my my instantaneous rate of change is approximately 75.1. So it would be 75.1 cubic centimeters per centimeter. Okay, because this is our unit for y and this is our unit for x, and a rate of change is always something per something. Okay, so now how do I do this for my strategy number 2? Same thing, I'm going to use a small h value. So I'm going to use h is 0.1. You can get even smaller. You could say it's 0.01. Again, the smaller you make it, the more accurate it is. So here, my instantaneous rate of change is equal to delta y over delta x. But remember, this time we said it's going to be f of a plus h. I'm just using the formula up here. F of a plus h minus f of a all over h. So I'm just using this thing right here. Okay, so this time what I'm going to do is I'm going to do f of, my a value is 5, it's happening at 5, my h value is 0.1, which means that I'm going to do f of 5.1 minus f of 5 all over my h value, which is 0.1. Okay, so then I end up getting, and sorry, again, this is an approximation, okay? So I end up getting, we know f of 5.1 is 132.651, and then f of 5 is just 5 to the power of 3, which is 125, all over 0.1. So then when I go ahead and do my subtraction right here, I get approximately 7.651 over 0.1, which is going to give me 76.51 cubic centimeters per centimeter. Okay, so those are 2 different strategies that we can use to find the instantaneous rate of change, actually just to find the estimate of an instantaneous rate of change until you get to calculus. Okay.